No, no problem. So I'm very pleased to have Marcelo presenting his PhD defense today. We were very lucky that when he was an undergraduate student, he came to Rice for a study abroad experience. And so when it was time to look at graduate school, he had various things pulling him back to the Houston area and to the Rice campus. And he chose to come and work in our group. And he's done some really interesting work in the area of renewable energy. He's also done some summer work, some internships with renewable energy as well, which I think has really helped to enrich this thesis work and his dissertation. So Marcelo, I will mute myself and I'll let you go ahead and take it away. And everyone, please stay muted unless you have a question during the presentation. Thank you.
Nice. Thank you. Thank you, everyone. Hello. Thank you for coming. And Dr. Schiffer, thank you for the introduction. Today, I'll be presenting my PhD work titled Hybrid Solar Energy Conversion Enabled by Nanoparticle Filtering. I'll start with an introduction, then I'll present on 3 stages of this dissertation, and then finish up with conclusions for the work, as well as future directions. Renewable energy generation in the United States has significantly increased in the past decade. From 2010 to 2020, the generation from renewables in the country increased 94%. And it's expected that renewable energy will generate up to 42% of the total energy in the country by 2050. More specifically, solar energy generation is expected to contribute with 47% of the total renewable energy generation, becoming the largest source of renewable energy domestically by 2050. The majority of the utility scale solar energy projects in the US are either photovoltaic systems where sunlight is converted to electricity using solar cells, or concentrated solar power, also called CSP systems. These CSP systems are either parabolic trough systems, where parabolic reflectors are used to concentrate light on a tube, contain a heat transfer fluid, or they're molten salt systems, where thousands of reflectors are used to concentrate light on a tower containing a material of high melting point, usually a salt, and that therefore the name molten salt. In my PhD work, I investigated spectral splitting concentrated photovoltaic thermal or CPVT systems capable of absorbing solar energy as heat and generating electricity using solar cells. This twofold energy harvesting capability has attracted interest from the scientific community, with many researchers investigating different approaches to achieve hybridization and also investigating the performance of these systems.
It has a list of participants. Can you select?
Can someone help me with the muting, please?
Yeah, I just muted him like as soon as I could find the picture. Sorry, it took a second.
No problem. Before we delve into the research related to spectral splitting CPVT systems, there are 2 concepts that need to be explained to understand the basis of my work. The first one is how solar cells generate electricity. When we talk about electricity conduction in bulk materials, we can characterize them into insulators, conductors, and semiconductors. In insulators, there is a significantly large energy difference, also called a band gap, between the valence band, where the electrons are bound to the atom, and the conduction band, where the electrons can be transported to other atoms. This large band gap between the valence and the conduction bands is what prevents these materials from conducting electricity at normal conditions. On the other side of the spectrum, we have conducting materials that have overlapping bands. They don't have a band gap like the insulators do, and the electrons can move freely in the conduction band. And this is sometimes referred to as the sea of electrons. Semiconductors, however, are materials that are somewhere between insulators and conductors. There's still an energy gap like we have in insulators, but this energy gap is considerably smaller. What that means is that given a minimum amount of energy equal to the band gap, the electrons in a semiconductor can be transported from the valence band to the conduction band, where they can become an electric current. The figure on the right-hand side shows how silicon solar cells generate electricity across the solar spectrum. Shaded in gray, we have the spectral irradiance, which is the amount of power coming from the sun. And in red, we have the energy that can be converted in the solar cell. As we move from longer wavelengths or lower energy regions to shorter wavelengths, which are higher energy regions, the silicon solar cell suddenly starts converting sunlight into electricity. That minimum energy required for solar conversion is again the band gap, which for silicon solar cells is around 1100 nanometers. The photovoltaic model used to calculate the power generated by the solar cells is defined by a set of 4 equations. It includes the dark saturation current, I naught, the open circuit voltage, VOC, the short circuit current, ISC, and the fill factor, FF. Some of the parameters used in this model include the solar cell temperature, TC, and the band gap that we just talked about, EG. The second concept is related to the absorption of light by nanoparticles. Nanoparticles can absorb radiation because of a collective excitation of the sea of electrons in a conducting material. The incident electric field causes dislocation of the electrons, and the positive charge left behind after the displacement attracts the electrons, pulling them back to the original position or trying to pull them back to the original position and causing an oscillation. Under certain conditions, resonance is established, causing an absorption of radiation and an increase in the particle temperature as the oscillations decay. That is precisely why we can use nanoparticles for solar thermal absorption. The transmittance of the nanoparticles in a fluid, which is also called a nanofluid, can be obtained by the extinction coefficient and the height of the fluid. The extinction coefficient of a nanofluid is the combination of the extinction of light by the base fluid, it could be water, for example, and the nanoparticles, which could be different materials. The light extinction by the nanoparticles depend on their volume fraction or the concentration, the same meaning, which here is represented by FVI, their size represented by DI, and the absorption efficiency, which here is represented by QAbsI. To calculate the absorption of radiation by nanoparticles, we need to obtain the cross-section, the absorption cross-section, which for small particles depends on the size of the nanoparticle, as well as on the intrinsic optical properties of the material and the base fluid, represented by epsilon I here and epsilon M. As an example, this figure shows the absorption efficiencies of different particle materials when the particle sizes are small in this case. Some particles absorb well in the ultraviolet, other particles well in the visible, and others in the infrared region. The overall system schematic of a spectral splitting CPVT system that uses nanofluids is represented in the figure on the left-hand side. The full spectrum solar radiation passes through a nanofluid filter that can absorb radiation at selected regions of the spectrum. The nanoparticles absorb energy and heat up the fluid that can now be used for heating other systems or generating electricity using a thermal system. The filter radiation is directed to the solar cells where it will be converted into electricity. The figure on the right-hand side shows the solar spectrum before and after the nanofluid filter, with the unfiltered spectrum on top and the filtered spectrum on the bottom. The first stage of my PhD dissertation describes a long-term analysis of a CPVT system that uses nanofluids. This work has been presented before during my master's thesis defense, so I'll only go over it briefly. This work was motivated by a lack of long-term analysis in the field of CPVT systems, although different system designs and types of absorbing fluids had been explored by researchers. The long-term analysis developed in this work provided a proof of concept for the application of spectral filtering CPVT systems in the small scale and highlighted the potential of these systems to reduce carbon dioxide emissions. The design of the CPVT system in this work is very similar to the schematic that I showed earlier. The main difference is the addition of a primary channel below the solar cells, which in this case is used to absorb any thermal energy generated by the solar cells. The fluid coming out of this primary channel is redirected to the secondary channel, where the nanoparticles in the system can absorb sunlight as heat. We discretize the system into segments or nodes by creating control volumes and apply the first law of thermodynamics to these control volumes to obtain the system temperatures. As an example, we created a control volume at the top surface of glass 1 that includes heat transfer rates due to radiation, convection, and conduction, arriving at this equation. Each node in the system is represented by an equation like this one, where a link between neighboring nodes is created. The solution of the system temperatures can be achieved by solving a linear system where the temperatures are obtained as a vector, in this case, vector x. We integrated the heat transfer model that I just described to a domestic water heating system containing a water tank, a pump, and a heat exchanger. An optical filter model based on the absorption efficient equations that I just showed is input to the photovoltaic model and integrated to the heat transfer and domestic water heating models. We selected the optical fluid filter based on the spectral matching between the transmittance of each nanofluid and an ideal transmittance window for silicon solar cells, which is represented in the figures as the dashed lines. The gold nanoparticles in ethylene glycol were selected for their better spectral matching with a volume fraction, or again, concentration of 10 to the minus 4. We perform a parametric analysis to understand the importance of different system parameters, and the selected values from this analysis are shown in the table. Using these parameters, we simulated the system performance during a whole year, and the figure on the right-hand side shows the temperature in the tank during every hour of the year. We analyzed two tank sizes, 287 and 500 liters, and for each tank, we created failure bars to represent a period of time when the CPVT system was not able to provide enough hot water for the whole household. We decided to use the larger tank because of the lower failure rate associated with it. We also analyzed the amount of energy stored in the tank and generated by the solar cells at every time step. As expected, the performance of the CPVT system is directly correlated to the amount of sunlight available. When we have clear sky days, the energy stored in the tank is cyclical but fairly constant from one day to the next. During cloudier days, however, the energy in the tank reduces more drastically and the solar cells generate less electricity. In conclusion, this work simulated the performance of a CPVT system applies to a household by integrating an optical filter, a photovoltaic model, and a heat transfer model that includes water heating. A nanofluid containing gold nanoparticles at a volume fraction of 10 to the minus 4 was selected for the better spectral matching. And we performed a parametric analysis to select the system parameters and simulated the performance using those parameters for a whole year. The system provided about 2,200 kilowatt hour of energy, which was used for water heating, and a net amount of energy of around 730 kilowatt hour per year. Finally, we evaluated the environmental impacts of the system in terms of the potential to reduce carbon dioxide emissions. If you'd like to learn more about this work, it's been published in the Energy Conversion and Management Journal. In the second stage of my PhD, I investigated the best nanofluids that can offer a better spectral matching in CPVT systems. In the previous analysis, we selected the nanofluid mainly based on the volume fraction of 3 types of nanoparticles. At that point in time, we had not explored the benefits of using more than one type of particle at the same time. So in this analysis, we searched for the best combination of nanoparticles using a more objective approach through optimization. This analysis was motivated by other works in the field that have highlighted the importance of a better spectral matching between the nanofluid filter and the solar cell being used. The reasoning behind having a better spectral matching is because solar cells are not as efficient in generating electricity at energy levels that are significantly above the band gap of the cell. And radiation with energy below the band gap would not be converted by the solar cell and should be absorbed by the nanofluid. And although researchers have explored the efficiency of different nanofluid mixtures, works that search for the best nanofluid parameters through optimization are still lacking. The system design investigated in the analysis the same as presented in the introduction, where we have solar radiation being partially absorbed by the nanofluid mixture and the filtered radiation being directed to the solar cells. We included 10 different types of particles in the optimization, as well as 3 different base fluids, ethylene glycol, water, and therminol VP1, which is a heat transfer fluid. All the particle materials were metals, except for indium tin oxide, or ITO, which is a semiconductor that has a tunable resonant frequency. We included the metal nanoparticles in the optimization using the equations for absorption efficiency that I described earlier and using experimental data from the literature. This is not the case for ITO nanoparticles, where we took a data-driven approach to obtain the optical properties for ITO. To include ITO nanoparticles, we looked at the relationship between the tin doping that affects the resonant frequency and the carrier concentration. We also looked at the relationship between the carrier concentration and the damping constant, which is used to obtain the optical parameters for ITO. We broke down the optimization into 3 different regions, region 1, 2, and 3. The idea here is that we would like to completely absorb radiation in regions 1 and 3 and transmit radiation in region 2. The ideal transmittance window for each type of solar cell has been previously defined in the literature, where for silicon solar cells, for example, lambda 1 is equal to 732 nanometers, and lambda 2 is equal to 1067 nanometers. After defining the size of each region, based on these values on the table, we ran the optimization using water, ethylene glycol, and therminol VP1 as base fluids. To create the optimization routine, we use the same transmittance equation that I presented in the introduction. But here we expanded that expression to calculate the amount of solar energy transmitted within a region of the spectrum defined by lambda 1 and lambda 2. Finally, we expanded that expression to the regions 1, 2, and 3. And again, the idea of the optimization routine is to minimize the transmission in the first and third regions while maximizing transmission or minimizing absorption in the second region. We also added weighing factors, W1, W2, and W3, to increase the flexibility of the optimization routine. And this is because the optimization routine does not necessarily need to be used exclusively to match an ideal solar cell filter, like we're doing here. So we can have a wider range of application. For example, if for a specific type of application, we would like to transmit more in the first region, we could increase the weight related to that region before running the optimization. We adopted a metric using in the field to calculate the efficiency of an optical filter, represented here by eta. And similar to the optimization routine, it calculates the fraction of energy transmitted in the 3 regions. As I mentioned before, we obtain optimal nanofluids for 3 base fluids in combination with 3 types of solar cells. In the figure showing the results, the solar spectrum is represented by the light gray. The darker gray shows the ideal solar cell window, and the lines represent the transmittance of each nanofluid across the solar spectrum. For silicon solar cells, all of the nanofluids can transmit above 55% inside the ideal cell window. All of the optimal nanofluids for silicon contain gold nanoparticles that can absorb energy around 520 nanometers. The nanofluids based on ethylene glycol and terminal VP1 also contain ITO nanoparticles that absorb infrared radiation. Because water is a good infrared absorber, ITO nanoparticles were not selected as optimal in this case. A nanofluid based on water had the best spectral matching for silicon solar cells with an efficiency near 40%. And the nanofluid using ethylene glycol had an efficiency of 39.1, and the one using terminal VP1 had an efficiency of 36.6%. For the nanofluid based on water, copper nanoparticles were also selected besides gold, since they can absorb energy below 520 nanometers. For gallium arsenide cells, a nanofluid based on water also had the highest efficiency, close to 36%, but the other nanofluids also had efficiencies above 35%. In this case, silver and ITO nanoparticles were selected for all fluids, and silver was selected rather than gold because it has a sharp absorption around 380 nanometers, whereas gold nanoparticles would be absorbing inside the ideal solar cell window. The dual junction cell, which is made of two semiconductors, gallium indium phosphide and gallium arsenide, mainly selected silver and ITO nanoparticles. In this case, the silver nanoparticles absorb energy right at the edge of the solar cell window, and ITO absorbs infrared radiation. These filters had the lowest efficiency in the study because of the short wavelength of the dual junction cell. This short wavelength caused other nanoparticles, such as gold, to absorb radiation inside the solar cell window and reduce their efficiency. The best nanofluid for the two-junction cell was based on terminal VP1 and had a maximum efficiency close to 34%. And terminal VP1 was selected as an optimal fluid because it has a sharp UV absorption below 350 nanometers. Last, we also explored a nanofluid solution for silicon that excluded gold and silver nanoparticles with the goal of achieving a cheaper filter. A copper and water nanofluid was selected in this case, having a maximum efficiency of 39.3%, which is close to the efficiency when it contains gold, which was 39.7%. In summary, in this work, we developed an optimization framework for CPVT systems using nanofluids that is flexible to the type of solar cell. A maximum efficiency of 39.7 was obtained for silicon solar cells containing gold and copper nanoparticles in water. We also obtained a filter for silicon that excludes gold and silver with a maximum efficiency of 39.3%. The best filter for gallium arsenide cells was composed of silver and ITO nanoparticles in water with an efficiency of 35.9%. For the two-junction solar cell, a maximum efficiency close to 34% was obtained for a fluid containing silver and ITO nanoparticles and terminal VP1. In conclusion, the optimization routine developed in this work provided a path forward to improve hybrid photovoltaic thermal systems. If you'd like to learn more about this work, it has recently been accepted into the Renewable Energy Journal and should be available soon. In the third stage of my dissertation, I investigated the cost of obtaining energy using spectral splitting or spectral filtering CPVT systems that use nanofluids. So until now, I have talked about two technical advances in the field. By first looking at the long-term performance and environmental impacts of CPVT systems, and second, by finding optimal nanofluid filters for these systems. And there have been many of these technological advances in the field in the past years. From using pure fluids and nanoparticles in fluids for solar absorption, to developing parametric analyses and models for these systems, to creating experimental setups to validate their performance. However, there's still a need for cost analysis of CPVT systems. Only recently in 2020, the first cost analysis was done to evaluate the economical feasibility of these systems. So in this stage, we applied a levelized cost of energy, or LCOE approach, to spectral splitting CPVT systems using some of the nanofluids obtained in the optimization work. This approach has been extensively used in the energy industry and is calculated as the ratio of the project lifetime costs to the project lifetime net energy generation. In our analysis, we compared the LCOE of a conventional parabolic trough system to spectral splitting CPVT systems using silicon and gallium arsenide solar cells. Now, when we're talking about the system design, we're not looking at the smaller scale, but rather talking about a solar field. The solar field in this work is composed of a series of parabolic troughs connected to a power block that produces electricity from thermal energy. A thermal storage unit could also be included in a power plant like this one, but in this work, we did not consider thermal storage. The conventional parabolic trough design is composed of mirrors used to reflect radiation onto an absorber inside a glass envelope. This absorber is usually made of metal, and it absorbs energy throughout the whole spectrum of sunlight. In this analysis, we proposed a modification to the conventional parabolic trough system, where instead of a metal absorber, we have a selective absorber containing a nanofluid and photovoltaic cells. This design is similar to the one I presented before, where concentrated sunlight is filtered by the nanofluids or by the nanofluid and directed to the solar cell. We created an algorithm to calculate the amount of energy generated by the solar field based on a model developed by the National Renewable Energy Laboratory. When developing the algorithm, we included the code modifications that reflect the design modifications that were proposed. Some of these changes included adding the parameters related to the selective absorber, such as the transmittance of the glass and the nanofluid, as well as adding heat loss multipliers to the calculation, adding the power generation by the solar cells, and increasing the parasitic losses associated with the hybrid system. The LCOE algorithm included an annual cash flow analysis of the project by considering the initial fixed costs, annual variable costs, and the annual net energy generation by the power block and the solar cells. We calculated the LCOE using a probability distribution approach where some of the input variables were taken as random variables. In total, we included 11 cost and technical random variables using data in the literature to obtain a range for the LCOE of each system. As an example, here are 3 of the random variables associated with the silicon solar cell degradation, the heat loss multiplier, and the cost of gallium arsenide solar cells. We also investigated the effects of a parameter called solar multiple on the LCOE values. The solar multiple, or SM, is a parameter that relates the solar field area to the size of the power block. When the solar multiple is equal to 1, the solar field generates just enough thermal energy at peak solar radiation to operate the power block. A solar multiple above 1 means that the solar field provides thermal energy sufficient to operate the power block during several hours during the day. A solar multiple value that is significantly above 1 usually leads to thermal energy being lost, since the power block has a maximum generation capacity. To investigate the range of the LCOE for each type of power plant, we varied the solar multiple from 1 to 3 using intervals of 1/4 and obtained probability distributions for each case. In this figure, The dots represent the mean values and the error bars represent the range of the LCOE. As we increase the solar multiple from 1 to 2, there is a significant reduction in the LCOE for the hybrid systems. The mean LCOE for the gallium arsenide system reduces from about 44 to about 20 cents per kilowatt hour, and the silicon system from about 41 to 22 cents per kilowatt hour. The initial large difference between the thermal-only system, which is the conventional system, and the hybrid ones is related to the presence of a selective nanofluid filter. The nanofluid absorbs less thermal energy than a conventional metal absorber, and because of that, it generates less energy at the power block. We can also note that there is a reduction for the range of the hybrid systems as the solar multiple increases. The distributions become tighter. This reduction is associated with the temperature sensitivity of the solar cells when generating electricity. At lower solar multiple values, the gallium arsenide power plant, for example, is highly dependent on the power production from the solar cells, since there's a lack of thermal energy. And this dependency is diminished when we increase the solar multiple value. When we continue increasing the solar multiple from 2 to 3, the figure changes a little. The LCOE for the conventional system actually increases. This increase happens because of an excess thermal energy being absorbed by the solar field when the power block has a capped power generation capacity. And because the thermal storage unit is not included in this analysis, there will be a waste in thermal energy. So the project costs that allowed for this excess thermal energy will cause an increase in the LCOE. The LCOE for the hybrid power plants continue to decrease, since now the thermal energy absorbed is sufficient to operate the power block during more hours of the year and more energy is generated. One of the most important results in this analysis appears when the solar multiple is increased above 2.75. At that point, the gallium arsenide power plant becomes the cheapest option with a minimum LCOE of 16.69 cents per kilowatt hour. The overall minimum LCOE for the silicon power plant was close to 18 cents per kilowatt hour, while the gallium arsenide plant had a minimum of 14.5 cents per kilowatt hour. This value is closer to the LCOE of a thermal-only plant with a minimum at 13.29 cents per kilowatt hour. To understand the LCOE results better, we looked at the energy generation by each power plant at different solar multiple values. For these figures, each type of power plant is represented as a row in the subplot, going from the hybrid silicon to the hybrid gallium arsenide to the thermal-only or conventional power plant. Each line color represents a type of energy, where PB means power block, PV means photovoltaic, and the total is the total energy generated. The shaded areas that go with the lines show the range of probabilities like we analyzed before. For the silicon power plant, the power block generates most of the energy. This is due to a higher temperature sensitivity of silicon solar cells, represented by the wider region shaded in red, and the lower nanofluid transmittance. And because the power block has a capped generation capacity, smaller gains can be achieved at solar multiple values that are larger than 2. The energy generation from the gallium arsenide power plant depends more on the photovoltaic system than on the power block. Because of that, this power plant is less limited by the power block capacity, and its generation can continue increasing at higher solar multiple values. Last, the thermal-only power plant is significantly limited by the power block capacity. This will minimize the generation gains for this power plant at solar multiple values above 2. In summary, in this last stage of the dissertation, we analyzed the economical feasibility of spectral splitting CPVT systems compared to a conventional parabolic trough system. A levelized cost of energy analysis was developed to bridge the gap between the technology development and a real-world implementation of these systems. The overall minimum LCOE obtained for a silicon power plant was 17.83 cents per kilowatt hour, and the gallium arsenide power plant had a minimum of 14.5 cents per kilowatt hour. The conventional parabolic trough had a minimum at 13.29 cents per kilowatt hour. We believe that the analysis in this work contributed to the real-world implementation of CPVT systems by comparing the ranges of cost and energy generation for conventional and hybrid systems. In conclusion, the work in this dissertation contributed to the improvement of CPVT systems in 3 different ways. First, a long-term analysis helped to better understand the performance of a small-scale CPVT system during a whole year and assess its environmental impact. If a system such as the one proposed here were to be implemented in just 10% of the households in the US, it would help reduce greenhouse gas emissions equivalent to more than 3 million passenger vehicles per year. Second, an optimization routine was developed to obtain better spectral matching for different types of solar cells and base fluids. A maximum filter efficiency of 39.7 was obtained for silicon solar cells, where gold and copper nanoparticles in water were selected as optimal. The optimization framework developed here is crucial for the development of higher efficiency spectral splitting CPVT systems using nanofluid filters. Third, we developed a levelized cost of energy analysis to investigate the ranges of cost and energy production of hybrid and conventional parabolic trough systems. The lowest LCOE for a hybrid power plant was obtained using gallium arsenide solar cells with an LCOE value of 14.5 cents per kilowatt hour, which is about 9% higher than the minimum cost for a conventional plant. The LCOE analysis in this work demonstrates the potential for real-world implementation of spectral splitting CPVT power plants. There are still some open questions in the field of CPVT systems that future studies should address. A multi-objective system optimization that considers the type of solar cell, flow rate, and the size of the storage tank, for example, could be developed to obtain the best operating parameters for a small-scale CPVT system. Another important step would be to create a life cycle assessment for the small-scale system to assess its environmental impacts more accurately. It would also be beneficial to include the manufacturing costs into the optimization routine to obtain nanofluids with the best cost to benefit ratios, although their manufacturing costs are still fluctuating as the technology develops. A nanofluid stability analysis should also be done to investigate the long-term performance of the nanofluids proposed in the work. And finally, the addition of a thermal storage unit to the LCOE analysis would be a significant addition to the field, since it would increase the competitiveness of the proposed systems. I have many people to thank for the support for the past 5 years. I would like to thank my family and my fiancé for their immense support. Pai, mãe, irmã e Marion, muito obrigado por sempre acreditarem em mim e nos meus sonhos. Eu nunca teria chegado aqui sem o apoio incondicional de vocês. I would like to thank Dr. Schaefer, or Dr. Laura Schaefer, for giving me the opportunity to join her research group and for being such an excellent grad school and life mentor. Thank you also to my lab mates and colleagues for always supporting me and providing me with invaluable feedback. Thank you also to Dr. Bayazitoglu, Dr. Hassanzadeh, and Dr. Norlander for being part of my committee. And thank you for the excellent teaching and research advice in the past few years. Finally, I would like to thank the funding from the Terracon Innovator Award through Rice University. I thank you, and I'll be happy to take questions.
Great, thank you very much. Clap, 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 great presentation. You do like the virtual clap. It's always so awkward to clap on Zoom, right? So good job with that. We'll open it up if anyone, oh, look, little clapping icon down there. That's fantastic.
Oh, I can't see anyone yet. So sad.
Oh,
Wait,
okay.
let me see.
It's in the participant window because I've been monitoring that for waitlist.
Okay,
so
cool. Thanks.
I'll open the chat too. All right, so we'll take 1 or 2 questions from people in the audience who aren't on the committee. If anyone has a question, probably the easiest thing to do is raise your hand and I will like scroll and call on you. Anyone has a question? I assume Marian speaks Portuguese, by the way, with that whole Portuguese thing you said to her. So.
Yes, she does.
Cool.
There's a question in the chat. Sorry.
Oh, in the chat. Oh, I didn't see that. Sorry.
Sorry.
Oh, Yildiz is here. Any thoughts on when these systems might start being implemented in the US? Is the question.
Yeah, so that's a good question. So the field is still a bit young. So I guess the field really started gaining traction in the past 10 years or so, which for research seems like a long time, but it's still a young field, right? I think it would be like interesting to see the developments because so the DOE, the Department of Energy, has been putting out applications for grants, especially for CSP systems. And their target goal right now is 5 cents per kilowatt hour because they want to compete well with photovoltaic systems, which right now for utility scale is about 5 cents. So I think it will be interesting to see if systems like these are being funded as well. They have been in the past. Hopefully they will keep being funded. And if they continue being funded, maybe in the next 5 to 10 years, we'll start seeing more experimental validation and implementation of these systems. There are, of course, some hurdles, some challenges to surpass, I guess, to these systems, especially by using like nanoparticles in the fluid. Like the stability problem is something that still needs to be addressed. But yeah, maybe in 5 to 10 years, depending on the LCOE that we can achieve with the systems, depending on any tax credits that might be associated with implementation of these systems, and depending on the funding that if it continues coming through like it has been.
Sorry, I was muted. Great, thank you very much. So unless anyone else has a pressing question, we will go ahead and move to committee only. And I will ask everyone else to please leave the Zoom room.
Oh yeah, let me say in Portuguese too. Pessoal, muito obrigado pela participação. Agora vai ter a banca com o pessoal da minha banca. Se vocês puderem sair aqui, depois dou notícia como foi tudo. Muito obrigado, valeu. All right, thank you.
I could totally have said that in Portuguese.
Yeah, I should have sent you a little like text.
I should have, yeah. I mean, from when we did that joint project in Unicamp, I learned enough to like order in a restaurant. And that's about it, not for more complicated things. So. So I'm gonna wait as participant list goes down. My screen is very crowded right now with the pictures and the participants and the chat.
Dr. Schaefer, would you like me to keep recording this or?
Yeah, I think that's fine to do that. And Yildiz, by the way, as everyone's getting off the call, and I think that we're almost all there. I'll take the glovers off in a second. I know that you got on right when the presentation was over. We're happy to